Hello, welcome to Lab 4 for stats 115 and 215. I'm Gigi Ken. I'm your TA for this lab. Um, so this lab is mainly talking about the second part of homework 2. So before our lab material, I'm going to give you some announcement. So first of all, homework 2 is due this Sunday, February 21st, 2021 by midnight. And after homework 2 submission, please finish the post-homework survey. We're going to give some bonus point associated with it. So please do that. And just to clarify, our lab hour is every Tuesday from 6 to 7:30 p.m. And Thursday 8 to 9:30 p.m. Our TA hour is every Friday 4 to 5 p.m. And Saturdays 10:30 to 11:30 a.m. So if you already watched this video or you attended the Tuesday lab, you don't need to attend to the Thursday lab. You can pick one to attend. But if you have questions associated to the homework or to the lab, to the lecture material, you can get to us both on the lab hours and on the office hour. We're going to be happy to answer your questions. So for today's material, we're going to talk about this machine learning parts. We're going to talk about KNN, ridge, lasso, elastic net, cross-validation, logistic regression, SVM, random forest. So before everything, we need to install these packages and load these packages. So if you have not installed these packages yet, you can use either install the packages or VLC manager install to have these packages installed. We're going to need them for the homeworks as well. So just a brief introduction on machine learning. So one of these most important function of machine learning is to do pattern identification. So there are two parts. The first one is classification. Second one is clustering. So classification is supervised learning. So that means your input should have already have labels associated with it, so that your algorithm can identify these predefined labels and learn from these predefined labels and its associated variables. Then if you input another data to it, it's going to be able to assign a class to that new input. Whereas for clustering, is unsupervised learning. So you don't have any predefined labels. You only use the data provided to identify the similarities and try to group them together. So such as the k-means and UMAP. So the first one we're going to talk about is the KNN. So you use the first use the first k closest neighbors for each member of the test set by comparing the variable x for training data to the comparable x. And based on vote using these neighbors, you assign a y to the test data sets. So k-nearest neighbor is one of the simplest machine learning algorithm based on supervised learning techniques. It assumes the similarity between the new case and available cases and put the new case into the category that is most similar to the available categories. It stores all the available data and classifies a new data point based on the similarity. This means when new data appears, then it can be easily classified into a well-suited categories by using KNN algorithms. KNN can also be used as for regression, but it's mostly used for classification. So here is a brief example of KNN. So we say like this a green circle as the new input, and if we set k equal to 3, so we take only the 3 nearest neighbors will be these 3. So these two red triangle is going to vote for red, and this blue square is going to vote for blue. So in this case, 2 is greater than 1, so this circle is going to be color red and be put into the same class as the triangle. The triangles are. And if we increase the k to 5, then we're going to have these 5 neighbors included into this voting set. So the 3 of these blue squares going to vote for blue, and the 2 red triangles going to vote for red. In this case, the circle is going to be colored blue. So the K is really important in KNN. So different K is going to give you different class of give you different predictions. So how to pick a good K? The answer is we use cross validation to get the K gives us the highest accuracy for test data. I'm going to talk about cross validation later. So let's proceed to another example of KNN. So here we're using the leukemia data set. We take only these 3 classes, the ALL, the AML, and the NOL. So before everything, we need to do some data cleaning. So we did some data cleaning, and because the leukemia data set is really large data set, it has several 30-ish something of the patients and thousands of genes. So so to save some computational power and to save time, we first did a PCA on this data set, and we take only the 20 most variable, the 20 principal components with the highest variance, so that we have a much smaller dimension, and then we split it into test data sets and the train data sets, and we store the labels into type train and type test. And then we use this train control function to specify a control, which we use the cross validation with actually it's a 5-fold cross validation. And we measure the metrics of accuracy. So we use this function train to train KNN, use method KNN to train k-nearest neighbor classifiers. And then the control is going to pick the best K for us. We set the K range from 1 to 10, and the control is going to help us to pick the best one from it. And then we use this pre-trained KM to predict the label for a test data set. And we used the confusion matrix of this prediction and the real labels of this test data set. And we can see from here, the classifier did a pretty good job classify the ALL and the NOL, whereas we see the accuracy is 100% and 100%. However, for the AML, 2 of them are misclassified as ALL and 3 of them are misclassified as NOL. Just one of them is predicted correctly. So it's not doing a very good job on AML. It's probably because there is a close like ALL and AML is very close together, and yeah, it's just probably because AML doesn't have a very dense cluster itself. But we want to see the accuracy, we got 0.6875, which is pretty good, because if our classifier is doing a terrible job, we're going to get something like 0.333. We have 3 classes. Yeah. So 0.6875 is still like an okay accuracy, but from this confusion matrix, we just know that AML prediction is not so good. So now we can proceed to linear regression and logistic regression. So linear regression is one of the aim of linear regression is to model a continuous variable y as a mathematical function of x, so that we can use the regression model to predict the y when only the x is known. So the function normally looks like this, like beta 1 plus beta 2x plus epsilon, which is an arrow. And beta 2 is a slope, beta 1 is interception. So here is a brief example. So if we have a data like showing above, showing below, we can first do a scatter plot. So the scatter plot can help visualize any linear relationship between the dependent variable, which is the response, and the independent variable, which is the predictor, so that we can see whether they have a linear relationship. We can see from this graph, without any without modeling anything, we can already see like these two variable has a pretty much fair good linear relationship. So now we proceed and we see we want to check the correlation. So correlation is a statistical measure that suggests the level of linear dependence between two variables. So correlation can take value between -1 to 1. If we observe for every instance where speed increase, the distance also increase along with it, then we'll see there is a high positive correlation between them. Therefore, the correlation between them will be closer to 1. In the opposite, if we see something like a -1 for correlation, we'll see a negatively linear correlation. If you see something like a value like 0, then this kind of suggests that there is no linear correlations between these two variables. And we'll consider correlation negative 0.2 to negative to positive 0.2 low correlation. So now we want to build a linear models. Now that we can see there's a linear correlation, a linear relationship between these two variables from both the scatter and the coefficient plot. We use this LM to fit a linear model between these two variables. So where we need two input, the first one is the formula and the second one is the data. So in this case, the speed is going to be the x, and the distance is going to be the y. So after we build this model, we establish a relationship between the predictors and the response in the form of a mathematical formula for distance. And we can see like the interception is negative 17.5, and the slope is 3.9. However, the standard linear model performs poorly in the situation where you have a large multivariate data set containing a number of variables prior to the number of samples, which means you have a really small sample size. So a better alternative is the panelized regression, allowing to create a linear regression model that is panelized for having too many variables in the models. By adding a constraint in this equation. So here I'm showing the ridge, lasso, and the elastic net as the penalties. So ridge regression shrink the regression coefficient so that the variables with minor contribution to the outcome have their coefficients close to 0. The shrinkage of the coefficient is achieved by panelizing the regression model with a penalty term called the L2 norm, which is the sum of the square coefficient. The amount of penalty can be fine-tuned using a constant called lambda, which is right here. When lambda equals to 0, the penalty term has no effect, and ridge regression will produce the classical least square coefficient, which is the classic linear regression. However, when lambda increases to infinity, the impact of the shrinkage penalty grows, and the ridge regression coefficient will get close to 0. And now we can talk about the lasso regression. The lasso stands for least absolute shrinkage and selection operator. So it shrinks the regression coefficient towards 0 by penalizing the regression model with a penalty term called L1 norm, which is sum of the absolute coefficient. In the case of lasso regression, the penalty has the effect of forcing some of the coefficient estimates with a minor contribution to the model to be exactly equal to 0, whereas the ridge can only make it close to 0. So yeah, this is the difference. And this means that lasso can be also seen as the alternative to the subset selection method for the performing variable. So Yeah, and the same as range, Lasso also has this lambda term. When lambda is close to infinity, some of this non-important coefficient is going to go to 0, and in that way we achieve the variable selection purpose. And ElasticNet produced a regression model that is penalized with both L1 and L2 norm. The consequences of this is to effectively shrink coefficients and to set some coefficient to 0, because it has both the ridge and the lasso property to it. And then how should we pick for lambda? We use cross validation to pick for lambda. We pick a lambda that gives us a lower test error. So now we can talk about what is k-fold cross validation. So in the k-fold cross validation, the original sample is randomly partitioned into k equal sized samples. Of the k samples, a single subsample is retained as validation data for testing, and the remaining subsamples are used for training. The cross validation process is then repeated k times, which each of the k samples used exactly once as the validation data. Then you average the accuracy of the validation accuracy to get the final accuracy, and from there, with different value of input, you will know which of the from this accuracy, with different value of input, you will know which value is the best. And now we're ready for an example of this this regression models. So let's use the Boston data for predicting the median house value in Boston suburbs based on the multiple predictor variables. So first, we randomly split the data into training set, which is 80%, and test set with 20%. And then we specify lambda into a sequence from -3 to 3 with 100 of them value inside. And then we use the ridge regression. We set alpha equal to 0, so it's a ridge regression in that way. And we use cross validation of 10-fold cross validation to find the best lambda. And this is and then we get the coefficient of each of the variables from this linear model. And then we predict, we use the ridge model to predict the outcomes of the test data sets. And we compare the actual value and the test and the prediction. We got a square R square of 0.76. And then to compare with the lasso, now we put alpha equal to 1 and still use the cross validation of 10-fold to find the best lambda. And in this way, after we find this coefficient and stuff, we see R square of 0.76, which is very similar to the previous ridge only one. And now we want to look into both. So we use the elastic one. Now we don't specify a lambda. So in that way, this cross validation is going to we don't specify the lambda. And this cross validation is going to find the best value for us. So after we did this prediction, we got like very similar 0.76. So we can see from and then we did a comparison between these three models, and we can see from here, yeah, they are pretty similar to each other. Yeah, they're like pretty similar to each other. And the best model is defined as the one that has the minimized the prediction error. which actually I think they're pretty similar. So yeah, and it doesn't matter. So now we're ready for logistic regression. So logistic regression is a predictive modeling algorithm that is used when y variable is binary categorical. So that is, it can take only two values like 1 or 0. The goal is to determine a mathematical function that can be used to predict the probability of event 1. So once the equation is established, it can be used to predict the y when only the x is known. Because for linear regression, y has to be a continuous variable. So when y is categorical, you can use logistic regression to model it. Here is so the logistic regression tell you the probability of one event is happening. So if you take the threshold of 0.5, and your probability is greater than 0.5, then you will classify that data point into class 1. If you have a event that happens have probability lower than 0.5, then you categorize that data point to class 0. So here is a function of how do you calculate the p-value and plot this sigmoid curve. But I'm not going to go detail into the math. So if you have some interest in how this is formulated, you can Google it online yourself. I'm just going to go directly into an example. Here I'm using the breast cancer data sets. And before everything, I'm selecting some, and I did some data cleaning ahead, and then before anything, now I'm kind of subsetting it into 70% of this data to for training. And if we plot this data with table, we see the information of this data. We see 0 has 300 something and 1 has 160 something. So 0 has like about like 2 times more than 168. So in this case, we have a sample imbalance. This can be bad sometimes, so we want to make this sample the sample size more comparable between these two phenotypes. So we did we resample this data, and we got a final training data of 311 for both of the phenotypes. And now we use the GLM and family equal to binomial to fit a logistic regression model. We want to predict the class in terms of all the variables. And this one is we want to predict the class in terms of only the B1 chromatin variables. So we can see from here, this one is the one with all variables, and this one is the one with only one variable. And we have an AIC that's much smaller in the previous one than the second one. And and for the second one, we have for the previous one, we have accuracy of 0.797, which is pretty good. And here is just another graph showing you what is the logistic regression and how it look like if you plot it out. So now I want to introduce you the support vector machine algorithm. Support vector machine algorithm is one of the most popular supervised learning algorithm, which is used for classification, but also for regression problems. However, this is mostly used for classification. The goal of SVM algorithm is to create the baseline or decision boundary that can segregate n-dimensional space into classes so that we can easily put the new data point in the correct categories in the future. This best decision boundary is also called a hyperplane. SVM chooses the extreme point that helps in creating the hyperplane. These extreme cases are called as support vectors. For example, in this graph is this one. And if we see, so if we see it from this graph, we can see these are the hyperplane, and this is the support vector. SVM can use different kernels to draw different decision boundaries. So transform the data and then draw a linear boundary and transform the space like this one, from this one to this one. It prevents overfitting. Yeah, and there are two types of SVM. So the linear SVM is used for linear separable data, which means if a data set can be classified into two classes by using a single straight line, then such data is called a linear separable data, and we'll use a linear SVM. And if the data is not able to be separated in using a straight line, then we call it a nonlinear separable data, and the classifier is going to call it a nonlinear SVM classifier. So for example, we have this data set, and we see that if we get, for example, if we give them like two lines here, both of these lines are able to separate the data into two classes. However, if we calculate if we calculate the margin between the vectors, the support vectors, which is this one and this one for the right line, and we'll see this margin is right here, so it's not like very long. But for this green line, the margin will be this one, and we'll get a much larger margin. So for the SVM algorithms, we need to find a line that gives us the largest. We want to maximize this margin, so we can better separate these two classes. Yeah, and the margin is calculated as the distance between the support vectors. And if a data is non-linear data, we cannot draw a single straight line. So we consider about like this image. So now we need to transform this a little bit. We let z equals to x squared plus y squared. And then we replot this data. Now we are able to see how we're able to use a linear plane to separate them. And since we are in a 3D space, it's looking like a plane parallel to the x-axis. So if we convert it into 2D with z equal to 1, then we got something like this. So we're basically before we're using we from this one to this one, we're actually is managing to make this data from 2D to 3D. And now if we get it back to 3D, this hyperplane is going to look like a circle on the x and y axis. Yeah, so like for example, if we have some data like this, and if we use a linear kernel, it's going to separate the data like this one. Where this is classified as type 2 and this is classified type 1, but actually this is not what we expected to separate them, because we know these are type 2, then this is type 1, and we're going to get a very small accuracy and a large error on this one. Whereas if we use the radial kernel, we're able to very well like get 100% good separation on this one. Yeah, so it's really important to know your data feature before you choose the kernels for SVM. Okay, so I'm going to proceed to random forest. So random forest is another popular machine learning algorithm that belongs to the supervised learning technique. It can be used for both classification and regression, but it's mostly used for classification. Yeah. It combines multiple classifiers to solve a complex problem and to improve the performance of the model. Random forest is a classifier that contains a number of decision trees on various subsets of the given data set and takes the advantage to improve the predictive accuracy of that data set. Instead of relying on one decision tree, the random forest takes the predictions from each tree, and based on the majority vote of the prediction, it predicts the final output. So as we can see from this graph here, the training set is separated into subsets. And each of subsets is going to be passed into one of the decision tree, and each of the decision tree is able to generate one prediction, and it's going to be like the majority of the vote is going to be the final prediction. And there are some assumptions for random forest. So since random forest combines multiple trees to predict the class of datasets, it is possible that some decision tree may predict the correct output while others may not. But together, all trees predict the correct output. So that means like maybe this tree is predicting like wrong one, but because this is like a minority, so we're not taking care of this. We don't really care about what this is, but we give like the one that's the majority. So yeah, it's still correct. Yeah, with two assumptions for this random forest. First one, there should be some actual values in the feature variable of the data set so that the classifier can predict accurate result rather than guess result. And second, the prediction from each tree must have very low correlation. So the prediction from this tree and all this tree should be relatively independent. And there are some advantage of using random forest. So first, it takes less training time as compared to other algorithms, and also it predicts output with very high accuracy. Even for large data sets, it runs really efficiently, and it can also maintain accuracy when large portion of the data is missing. So the last point is the main reason that random forest gets so popular. Especially for some of the data, you have a lot of missing values. Random forest is the one that it goes for. I'm not going to just read these steps. It's not really useful. Okay, so let's just jump into this example here. So suppose there's a fruit basket, and you're giving this fruit baskets to a random forest classifier, and the data set is going to be divided into subsets and give to each of these decision tree. And during this training phase, each decision tree is produce a prediction result. And when a new data point occurs, then based on the majority of the result, the random forest classifier predicts the final decision. So it's like when you have this fruit basket, you subset it into 3 subsets, and you give them to each of the tree, and these 2 trees predicted to be apples, and this one predicted to be banana, and then you take the majority, which is apple, so you predict this to be an apple tree. I mean, yeah, an apple. I think this example is actually not so good. So let's proceed to the better one. So here I'm using the iris dataset instead of, yeah, we're really using a real dataset, the iris one. And we use the random forest. We first subset into training and testing, validation, and then we use the random forest to predict the species based on all variables. And we use 100 trees to do this. And then we want to see how does our classifier do, how is our classifier doing. So we can see it's got 100% for this Setosa, and it's also doing a pretty good job on this other two. So that kind of showing us that our random forest does work for this one. And then we test whether our random forest is doing a great job on new data sets. And we can see it indeed doing a really good job. It predicts this Setosa 200%, and it predicts the Virgi. Yeah, this one's also 100%, right? So yeah, also doing pretty good job on this one too. So it's saying that our random forest model is not only having a low bias, but also having a low variance. And now I want to just plot the ROC curve. So we can see we did a pretty good job too. Yeah, with the accuracy of 0.99, 0.99. Question?